So I want to make contact with Achim's lecture and give a little context to sort of what's going on and what we're thinking about. So this lecture is going to be called Prismatic Cohomology and K-Theory. And we've sort of been creeping up on this topic from two different directions. I explained yesterday how to actually compute THH in some simple examples using this kind of what I called this Gauss-Manin connection. And that was an absolute calculation of THH from relative calculations. At the same time, Achim has explained this theory of prismatic envelopes, which is very effective in relative situations. So, the background, maybe one of us should have at some point said this, the background for all of this work is our joint goal to compute the K-theory of rings like Z mod P to the N. And so I want to explain today the strategy for doing that, and that's going to make, I think, quite clear the calculations that Achim is doing. So K-theory of Z mod P to the N. This is, and really more generally, the K-theory of OK mod pi to the N, where K is a finite extension of QP, OK is the ring of integers, pi is the uniformizer, or a uniformizer. And computations of this sort are, people have wanted to do it for a long time. We've not completed the calculation, but we've reduced it to something that one can plug into a computer using these prismatic envelopes. Okay, so for any given group and enough computational power and time, one can compute any given group here. So let me give a couple reductions to this. So first of all, this is classically known. I think it's first attributed to Adarami Kuku, and it's just that these groups are finite. So each KR of OK mod pi to the N is finite for R positive. These are local rings, so K0, by the way, is just always going to be isomorphic to Z. The negative K groups vanish. So we're interested in computing some finitely generated abelian groups, okay? And so that's should be possible to do. Okay, what's the next theorem? Some of this is going to be sort of background on K-theory. The next is Gabor rigidity, which says that, it says more generally that if that there's an equivalence between the K-theory of R and the K-theory of R mod I with L-adic coefficients when Ri is a Henselian pair. And I think technically this is really true for connective K-theory. Okay? And L, sorry. And L isn't, it's L. Good. And so this immediately reduces the problem of computing the K-theory of OK mod pi to the N. Well, we already know what the K-theory of OK mod pi to the N modulo pi is. That's Quillen's calculation of the K-theory of finite fields. Yes, please? Excuse me? I was busy catching this. Well, quasi-excellent, gosh. Yes, it's a finite type over ZP. In the statement of Gabor rigidity, God. Okay, yeah, I don't think so, yeah. Sorry, it does have an easy, why is that true? you know, roughly speaking, what is K-theory, you know, built from in the classical approach? Well, you start with this infinite general linear group. This is true for any finite ring, really. Okay, you start with this BGL and you do this plus construction. Okay, to it. That's one way of computing the positive part of K-theory. Well, this is an infinite general linear group, but there's some homological stability to reduce the homology of this in any finite range to a specific BGL n R of OK mod pi to the n. Now this is just a finite, this is the classifying space of a finite group. In particular, it has finite homology everywhere. And you can use that and some sort of Sayre spectral sequence argument to eventually get that the homotopy groups of this space have to be finite everywhere. No. I'm glad you asked so that I had the chance to say that. So this is kind of an original use of homological stability, really. Any finite ring. Yeah, I guess probably if you have a connective ring spectrum with bounded homotopy, all of whose homotopy groups are finite, maybe it's also true. Except that, to be quite honest, I don't know for sure homological stability in that generality, but maybe it's true. I think that would at least have to be checked, but I don't know off the top of my head. Okay, fun questions. So this connective K-theory, so now in our case, what that means is that with L-adic coefficients, prime to this P up there, this is the same as the K-theory of the residue field, which I'm going to call FQ, with ZL coefficients. And this is computed by Quillen. This is just the K-theory of finite fields, or the L-adic part. So yeah, let me introduce just a little bit more notation here. Q is P to the F if we need it later. Yesterday, the residue was not finite. It is today. Much of what I'll say won't require the finiteness, but definitely, yeah. Yeah, precisely. Okay, so this immediately says that, well, first of all, we're interested in finally generated abelian groups. They're even torsion for a positive degree. So that we can just study them by their L-adic completions for all L, and then their P-adic completion. So now it's enough to, so now we want to study the K-theory of OK mod pi to the n with P-adic coefficients. And if we can understand this, then we're done. We'll have computed the structure of the K groups of the rings. And this is by far the hardest part. So how do we understand such an object like this? Well, that's the next theorem, which somehow we've gone through a conference on K-theory, and it's like day 3, and this hasn't been explicitly stated. Someone should talk to the speakers. So Dundas, Goodwillie, McCarthy, came up with a theorem to control the difference in K-theory in general when you have nilpotent extensions. And this is an example of a nilpotent extension. OK mod pi to the n is obviously a nilpotent extension of the residue field, FQ. That's maybe one of the features of doing this mod pi to the n. And so their theorem is that if R to R mod I is a nilpotent extension, then the following square is a pullback square: the K-theory of R, the TC of R, the K-theory of R mod I, and the TC of R mod I. And in our case, what this means is TC of a p-complete ring will already be p-complete. So we don't really need to p-complete on this side. It means that and this is a pullback square, not just some random square. The K-theory of OK mod pi to the n fits into a pullback square, with p-adic coefficients, fits into a pullback square with the TC of OK mod pi to the n. The K-theory of the residue field, FQ, with p-adic coefficients, and then TC of the residue field with ZP coefficients. Oops, before it gets away from me. Okay, so there's a pullback square like this, and well, the bottom term is actually a connective cover. So by Quillen's calculation, K-theory of FQ is with ZP coefficients. Well, remember, all of the higher homotopy groups are prime to p torsion in Quillen's computation of the K-theory. So this is actually just equivalent to the Eilenberg-MacLane spectrum ZP. And TC of FQ, FQ, well, we don't really need to say with ZP coefficients. This is computed by Hesse-Holt and Madsen, and this is, well, I'll just say that the connective cover of this is also ZP. There's no higher homotopy groups. Is there a question? And so what does that tell us about this pullback square? Well, it actually tells us that the K-theory of OK mod pi to the n with ZP coefficients is equivalent to the connective cover of TC of OK mod pi to the n. And so now what we've done is we've reduced this entire question, which in principle has to do with like the homology of these infinite groups and this complicated plus construction, or this complicated sort of group completion in the world of E-infinity spaces. We've reduced that to a sort of homological calculation involving topological cyclic homology. Okay. Any questions? Well, this TC of these p-complete rings, oh, sorry, maybe it's confusing. I'll just erase this. Or I could put it in. It's already p-complete. Sorry. So this means p-completion when I write it like this. But of a p-complete ring, the TC is already p-complete. So one doesn't have to do anything. Okay? And so now, we've reduced this classical calculation to something involving topological cyclic homology. And just if you're new to this sort of philosophy is just called trace methods, because we're taking some sort of trace functors out of K-theory, and you see here why it's so effective. Any other questions? A finite extension of QP. Oh, I see. Yeah, for this, what would we? Yeah, right. Any discrete valuation with perfect residue field, I suppose. P-complete discrete valuation with perfect residue field would work. Well, and you don't even need P-complete if you're doing this mod pi to the n. How do I get this? Well, I'm saying that this is basically an equivalence, right? So it's a pullback square, but if the bottom is an equivalence, the top is an equivalence as well. There's just a little haze. This has homotopy groups in degree -1, but that's the only obstruction. Okay. Any other questions? I could. And I will do so tomorrow when I talk a little bit about Selmer K-theory. The comment was a suggestion that I talk about Clausen-Matthew-Morrow rigidity, which is a sort of a simultaneous generalization of Gabor rigidity and this Dundas-Goodwillie-McCarthy theorem. But I'll get to that at a later point. Okay, any other comments or suggestions? So now we have to compute this TC. And remember, okay, so let's see. So this is 4.1, this prismatic cohomology and TC. 4.2. And you know, classically, these TC calculations were pretty tricky. And that was partly because we didn't have a good way of breaking it down into small chunks. And so this motivic filtration is exactly a way of breaking this down into small chunks. And you know, so that's what I explained a little bit in a previous talk. If you know, we have a defining fiber sequence for any R quasi-symptomic. So here R will be quasi-symptomic in the sense of lecture or something. And there's a fiber sequence and this is given by this can minus phi map induced from the cyclotomic structure. And what Bott-Morrow and Schultz observed is if R is quasi-regular semi-perfectoid, then these two terms are even, i.e. concentrated in even degrees. And they used that to define basically a cohomology theory in the quasi-regular semi-perfectoid case, and then they unfolded it to give. They right con-extended, or they used descent to get a cohomology theory for general quasi-symptomic rings. And so the way that that works is that they just defined in this case pi 2I Tc minus R over Zp is by fiat basically this nth stage of the Nygaard filtration of absolute prismatic cohomology of R. Broicus and twisted by I, and I'll make contact with Akim's lecture in a moment, and pi 2I of TP, R over ZP is well, we just forget the Nygaard filtration. And so then they use this to define a filtration on TC, okay? So in degree 2I, we have a map from here to here, and then and then they defined in this quasi-regular semi-perfectoid case, they defined the ZPI of the quasi-regular semi-perfectoid. So, you know, suspended up by 2I to be equal to the fiber of this can minus phi, but just restricted to the 2I homotopy groups. Okay. Right. Let me explain why I did it in this specific way. Now unfolding, one gets filtrations F star. I'll just call it mote on TC, TC minus, and TP for R in quasi-syntonic, and the graded pieces are now, well, ger I mote TC minus R. This is by fiat the n more than or equal to I Nygaard filtered piece of Nygaard complete absolute prismatic cohomology, Breuer-Kissen twisted by I, and then suspended by 2I, because here we're taking a 2ith homotopy group. So when we take the double speed Postnikov tower, the ith graded piece is this abelian group sitting in 2I, suspended up by 2I. Similarly, GR I TP is equivalent to this prismatic cohomology, 2I. And I've done it this way so that GR I mote of TC minus, of TC R is this symptomic cohomology sitting in 2I. Okay. So no? Sorry. Did I Oh, yeah. Sorry. Yeah. I was getting fancy. Okay, sorry. Yeah. Thanks. Okay. So one does this. So what's the strategy for quasi-regular semi-perfectoids? These are even, and you just take the double-speed Postnikov tower, and the ith graded pieces are just some homotopy groups shifted into some degree. Now for TC, it's not quite true that it's literally even. Instead, it's this fiber. Okay, so there could be some stuff in, this could have some degree 0 and some degree 1 cohomology. Okay, although it turns out later that sort of as a quasi-symptomic sheaf, it is concentrated in degree 0, but that's a harder theorem. Okay, and so you have this motivic filtration this way, and they just you can just take these to be definitions of these symbols. For the time being, that's the original construction. Now the goal is, of course, if we can compute, so this is called symptomic cohomology. Symptomic cohomology filters TC, and if we come back to our goal of computing the K-theory of OK mod pi to the n, if we can compute the symptomic cohomology, then up to a spectral sequence, we're done. Okay. Any questions? Yes? Yeah. Okay, it's Noetherian. I agree. So far, everything you've said. Okay, mod pi to the n, yeah. Sorry, the question, it was a comment. These are Noetherian rings. Okay. Well, I mean, in this calculation that I'm discussing, K will be finite. In the process of passing and connecting these to prismatic cohomology, we're here using this quasi-symptomic site, and where we compute by passing to some huge ramified extension and then descending. Okay, so does that answer the question? Okay. So now these are just words, or well, okay, maybe not so many words, but symbols. What does this have to do with what Achim was talking about yesterday? So Achim gave us an explanation of this prismatic site, and this prismatic site, R over A sort of prism, where A is a prism, and R is an A mod I algebra. So this is sort of opposite to diagrams like this. where this is a delta ring map, and this is a prism as well. And so this is a site with the p-adic flat topology on B, and there's a structure sheaf which takes a diagram to B. That's the structure sheaf. And so when I take R gamma of this site with values in this structure sheaf, this O prism evaluates a diagram like this to B, then that's defining the prismatic cohomology of R relative to A. And this is really sort of the site-theoretic prismatic cohomology. And there's some sort of various different flavors. It's probably better to take the site-theoretic definition in the case where you're smooth over A mod I, and then to left extend that to arbitrary A mod I algebras. But then it's a theorem that when you do that, that derived prismatic cohomology agrees with the site-theoretic prismatic cohomology as long as you have some quasi-LCI properties over B mod J. So when you have some restriction on the cotangent complex. So we're not going to worry too much about the possible definitions between the different flavors here. But now there's an important variant of this. Here on the right-hand side, there's no ambient prism in this notation. This is just prismatic cohomology of R, bare prismatic cohomology of R. And how do you get that? Well, that's the absolute prismatic site. And there you just sort of drop A. Diagrams like this, where this is a prism. And again, you have a structure sheaf which evaluates such a diagram to B, and then the absolute prismatic cohomology of R is going to be the cohomology of this site with values in this prismatic structure sheaf. And again, there's also this O prism bar, which is the quotient by the sheaf J, and there's absolute, and that's corresponding to prism bar here, and there's also some prism bar, some absolute prismatic cohomology bar. So this is what appears here, or at least almost. There's this additional Nygaard completion here, which just means that, which is right. So one of the key ideas in our paper and is a sort of conceptual union or amalgamation of these two sites. And the idea is, if you just stare at this prismatic cohomology on the left-hand side, there's just no reason whatsoever for A to be a prism. Okay? So now let's just let A be a delta ring, and R a commutative A algebra. We tend to call such pairs A comma R delta pairs. It means that A is a delta ring, and R is an A algebra. It doesn't have a delta ring structure. Okay? And now we can make the same, literally the same definition. Nothing changes. Where this is still a prism. So B is still a prism, and we still take commutative diagrams like this. And this leads to a prismatic cohomology relative to delta rings as the cohomology of this relatives of this site with cohomology of the structure sheaf. What's an example of this? I'm going to give two examples to connect to a couple different things. Yes? Correct. Right. So this, in BMS2, this was used to define these terms. And then in the paper of Bott-Schulze, they made this site-theoretic definition, and then they checked that those two agree. After Nygaard completion, yeah, yeah, exactly. And maybe I'll make a note, maybe I'll just make a remark here so that we can kind of, ignore this completion business a bit. The remark is that ZPI-R is also quasi-isomorphic to the fiber of the non-complete version. Of absolute prismatic cohomology. So somehow this, if you like, this can minus phi is an equivalence at infinity, and so we can just ignore that. We can ignore the difference between these if we want. I mean, maybe that's helpful for you, maybe not. So what are a couple examples? So this is just a perfectly good category. We just don't require A to be a prism. But this still makes sense. So what are a couple examples? Well, absolute prismatic cohomology, written this way, this is the same as, well, I even say it differently. The absolute prismatic site up there, well, this is just equivalent to the relative prismatic site over the delta ring ZP. ZP is the initial delta ring. So I can view it as living in here behind a curtain, or not. And so these sites just agree when I put A equals ZP here, and as a consequence, that means that the absolute prismatic cohomology of Bott-Schulze is the same as this sort of relative prismatic cohomology over the delta ring ZP. And so this is one example. It should be maybe, okay, I haven't checked it for derived commutative rings, but at least for any animated commutative ring, it's fine. And maybe as a sanity check, one way to sort of think about this is that Bott and Matthew proved that for regular Noetherian rings, that the absolute prismatic cohomology is already Nygaard complete. So somehow there, you wouldn't have a difference anyways. And then we proved with Morrow, Matthew, and Nicolaus that this is left conextended in P-complete objects from smooth ZP p-adic completions of finally generated polynomial rings over ZP. So that's another way to sort of see it. Okay. So another example here is, is prismatic cohomology, the relative prismatic cohomology. Sort of, I'll write it in this illuminating way. So this will be, if R is an A mod I algebra. What does this mean? What I mean is that this, in the case, if R and A is a prism, and A is a prism itself. So if A is a prism, and R happens to be an A mod I algebra, well, any such commutative diagram, well, I should have said this is still a delta ring map. Any commutative diagram means that I has to map into J, and then by the rigidity property for prisms that Achim mentioned, that just means that this is a map of prisms, and that J is really induced up from I. Okay, so this simultaneously generalizes the absolute prismatic site and the relative prismatic site of Bott and Schulze. Yeah, precisely. Yeah, I've sort of overloaded the operators, and I'm saying that they're the same. So let's call this like R over A delta and R over L delta here for the moment. Okay. So this recovers some other things that that we're interested in, but it has a little bit more functoriality that was not manifestly present in the original approach to prismatic cohomology. For example, it's going to tell us that this prismatic cohomology is functorial for delta ring maps and not just for prisms, for maps of prisms, and that's going to be important in a couple minutes. Okay, so what? Yes. How am I going to do this? Here's maybe just a little taste, and we'll come back to this for why you might sort of think that such a thing should exist. Well, let's return to this object, this sphere spectrum as adjoint Z, and let's look at a discrete commutative ring R with a map like this. So Z maps to some element pi. Now, if R is a Z adjoint Z modulo some uniform, well, okay, maybe ZP adjoint Z modulo some uniformizer Z algebra. Okay, so this is the prismatic case, right? Then, well, so we have THHR relative to S adjoint Z, so I explained this in my last talk. This is something that makes sense, and I can consider the corresponding TCIR over S adjoint Z and TPR over S adjoint Z. And Bott-Morrow and Schulze proved, well, in combination with Bott and Schulze to compare to the absolute prismatic site, that these admit filtrations with GER I TC minus R over SZ being, well, now it's the relative prismatic cohomology R over SZ, R over this prism, ZP power series Z, Nygaard completed, and GER I of TP, not sure why I'm at the bottom of the board here. This is the Nygaard completion of the Frobenius twist that came up in Achim's talk. I mean, I should replace this with Witt vectors of the residue field. Sorry. Okay, so again, we have a connection between now relative prismatic cohomology. So this is R relative to a prism. This is R relative to a prism. We have a slightly different looking picture here. Here there was no Frobenius twist. Here there is a Frobenius twist. This Frobenius twist, what is it? Well, it's so recall this Frobenius twist. This is the prismatic cohomology of R over A, base changed over R, base changed over A along the Frobenius here. Okay, so but this perspective of prismatic cohomology relative to delta rings is very nice because it explains that these are the same symbol, right? Because prismatic cohomology now, R over ZP, Frobenius twisted by 1, so that's the same as prismatic cohomology of R over ZP in this delta ring theoretic sense, tensored over ZP with the Frobenius on ZP, but that's the identity. So nothing's changed here. So this is the prismatic cohomology of R over ZP, and that's the prismatic cohomology of R. And so you see, somehow we're explaining why there's this difference in how these filtrations looked in BMS2, where in the absolute case there was no Frobenius twist, and in the relative case there was a Frobenius twist in the associated graded of the motivic filtrations. And that difference is explained by the fact that, well, there really is a Frobenius twist, it's just trivial, because we're working over ZP. Okay, so that's a nice, I guess for some reason I'm just giving a pitch for this perspective. But why might you think it should exist? Well, here we can, this object just exists for any S-adjoint Z algebra. We didn't need R to be an algebra over a prism. Like, we didn't need R to be an algebra over a quotient like this. It just makes sense in general. Okay. So there's this TC, so these terms just make sense for any E infinity R algebra. Okay. And so that might lead you to hope that you could understand this, this theory in a little bit more generality. Okay. So we're gonna come and sort of merge these two perspectives here in a second. For this, see the relevance for this absolute versus this relative picture. Any questions? Yeah, right. I think under some mild hypotheses, there will be a filtration on this TP, even in the non-prismatic case, where the associated graded is this relative, something related to this relative delta theoretic prismatic cohomology. Is that the sort of thing you were asking? Yes. Oh. That's right. So there should be a kind of corresponding theory. So we were talking about this before the conference. Roughly speaking, to any E infinity ring which is flat, connective E infinity ring which is flat over the sphere. So for such a thing, the Tate-valued Frobenius gives you sort of a delta ring structure on pi 0, and there's sort of and then there's a corresponding prismatic cohomology relative to that delta ring, which should be connected to relative TC minus and TP. So that, I don't believe you can always go back. So, but to be quite honest, we have not worked out all of the details for that correspondence. So, okay. So now let me just draw a picture of what's going to go on, of what's going to happen. So symptomic cohomology, motivic spectral sequence. So I have this filtration on TC of a quasi-symptomic ring, and the graded pieces are these symptomic complexes of R shifted by 2I, and I get a spectral sequence indexed using the same conventions as my first lecture, HS minus T, ZP minus T, symptomic cohomology of R, converging to TC minus S minus TR with ZP coefficients. And I just wanted to draw a little bit about how that looks and where the interesting stuff is going to be for us. So a theorem of myself, Akil Matthew Morrow, and Tomas Nikolaus says that says that for R quasi-symptomic, or well, maybe just for R period, well, it says that HS of ZPTR is 0 for S more than T plus 1. And also for S equals T plus 1 if R is what's called strictly W local. And for us, this e.g., just a strict tensile local ring. Okay. So this gives us a vanishing on the cohomology. And for R quasi-symptomic, we also have that HS ZPT R is 0 for S negative. And we also have in general that these complexes ZPT are 0 for T negative. Okay, so those are the sort of three things that one uses to get some handle on this. And so let me just draw this spectral sequence kind of to compare to what we saw with this motivic spectral sequence the other day. So H00, which is going to be the degree 0 cohomology of the 0th symptomic complex evaluated at R, that sits here. H10, H11, and of course I'll need your help again, I'm sure, as I start to mess this up. Okay, so far no one's screaming yet. Maybe only inside. Okay, and so forth. And this theorem of ours gives us a vanishing line right here. Okay, so this is all 0. And then because the cohomology is really cohomological, there's no negative cohomology. This is sort of an analog of a Quillen-Lichtenbaum, or a Bailenson-Soulé type vanishing, but it's easy here. It's nothing special. And so we get everything is concentrated here. A little bit of structure. So this is contributing to TC minus 1. This is contributing to TC0 and so forth. This is TC1. Make it a little easier to read. This is what I would like to call the perfectoid line. Or even really, yeah, so for a perfectoid ring, or even quasi-symptomically locally for a quasi-regular semi-perfectoid ring, everything would be concentrated in these two terms. So these are contributing to TC0, TC2, TC4, and so forth. And it turns out that for the rings that we're interested in, everything is concentrated in the part we care about is really going to be like this. Each weight, that's the rows, will contribute at most 2 homotopy groups. Okay. And from that, you immediately, so we're gonna prove that the symptomic cohomology is concentrated in this trapezoidal region for OK mod pi to the n. And from that immediately implies that the differentials, which all look like this, are going to vanish. Those are the D2 differentials. So in this case, the differentials will vanish, and there will be no possible extensions. So once we've computed the ZPIs, we're done. So this is the region of relevance for OK mod pi to the n. Okay. That's something we have to prove. I'm not saying that's something that you should be seeing immediately. Okay. So now there's two tricks to get the computation really going from this point. Okay, let me pause and ask if there are questions while I erase. And also move the board. What was that? Well, I guess I'm just saying that for a perfectoid, like a ring like OCP, that everything except for that line is 0. And that's also true for for characteristic P, quasi-regular semi-perfect rings. And it's philosophically true in general for quasi-regular semi-perfect rings, but only literally true locally by this theorem of Bott and Schulze. Okay, any other questions? Okay, so now let's say 4.4. What's helpful to know, at least this is somehow, I find this philosophically helpful, is to have an a priori bound on the range of these ZPIs. So I guess we've been calling this sort of technique crystalline degeneration. And it harkens back to this extra filtration number 4 that we had yesterday, right? OK mod pi to the n, this is a filtered ring, is a pi-adically filtered ring. What's the associated graded? So the graded of this ring is FQ adjoins Z mod Z to the n, one of the most studied rings in K-theory. And the K-theory of this has been computed again and again and again and again. I was even going to do it today, but maybe I'll spare you. And realistically, I don't have the time. So this is a filtered ring, and its associated graded is this graded ring. And so using this, everything in sight picks up an extra filtration. You can prove that either by introducing a sort of filtered notion of these sites using the idea of filtered delta rings that Achim explained, or you can do something more sophisticated and work with these sort of W-cart stacks over A1 mod GM. But for this, we're just gonna, you'll just have to believe me. So so everything picks up a filtration. Which we'll write F star, yeah, I'll write it F star ZPI, and maybe now this ring will just be R. And similarly for the absolute prismatic cohomology and everything else. And part of the point of this is that the associated gradeds of these F filtrations, I'll just say it for symptomic cohomology, but it's true for the other ones, the associated gradeds are isomorphic to the associated gradeds of the sort of corresponding F filtration coming here from the Z-adic filtration on ZPI of FQ adjoins Z mod Z to the n. It turns out that these filtrations are complete, so we can completely sort of understand them from the associated graded, and we can use that to get some a priori bounds on the location of the cohomology of the complexes that we care about. Okay, so we also have, I'll write this, so we also have GR star F prismatic cohomology, how is it R? And so on for all of these theories. And so the nice thing about that is you can see this is into the crystalline case. This is a characteristic P ring, and so you can just compute this directly via crystalline cohomology. This is even a better situation. This ring lifts to characteristic 0, and it lifts with a lift of Frobenius, just to the ring ZP adjoins Z mod Z to the n, where Frobenius takes Z to Z to the P. So this lifts to characteristic 0 with a lifter Frobenius, which means that you can just directly write down the prismatic cohomology in terms of a de Rham complex. And you can also write down the Nygaard filtration in terms of that complex and everything. And when you do, you get some complex. It looks a little complicated, but you can just pick out exactly what happens in each weight and just compute everything that happens. Okay. And what you do when you see that is that, yes, sorry. Yes. Well, okay, which is the same as the associated gradient of the z-adic filtration. Yeah. Yeah, sorry. Thanks. Exactly. Yeah, it's just, I mean, this is even better. It's graded, so it somehow has even more structure. So the upshot is when you use this crystalline degeneration, it tells you things. It tells you a couple things. So first of all, it tells you the location of the prismatic cohomology. So first, it tells you that, and this isn't the only way to see this, but it's a way that I like. It tells you that, that the absolute prismatic cohomology of R is concentrated in cohomological degrees 0 and 1, and that's true with any Nygaard twist, any Breuil-Kissen twist, and the same with prismatic cohomology. It's in DZP minus 1 to 0. And together, these, of course, immediately imply that ZPI of R is in the derived category 0 to 2, minus 2 to 0, because it's a fiber of a map between these two terms. Okay, so the worst thing that could happen is that we could be not surjective in degree minus 1, and that would create degree minus 2 homotopy. So we've immediately severely restricted the region that we're working in the spectral sequence. And it actually turns out that we can do just a little bit better. Right. It turns out we can do a little bit better. Namely, for I positive, then in fact this is in minus 1 to 1, this is in minus 1 to 1, and this is in minus 2 to minus 1. Okay, I think just for purposes of time, I won't say more about that, but this is a sort of simple argument that you use using this crystalline degeneration method, and you just check it for here. And so let me give a reference. Yuri Salima has a great article where he just sits down and expands on an idea of Akil-Matthew to just compute everything in sight in this case. And there's just elements. It's specific elements and differential forms, and you just do it. And it's kind of a feeling of the work that Akim was describing yesterday. So let me just say a couple more words. Now we have some kind of control of these complexes, and we want to bring everything together. And the main idea to do so is to try to tweak what we talked about yesterday. Yesterday we successfully controlled the absolute THH from this fiber sequence using the relative THH. Now, we don't quite know how to do that, but instead we can use this idea of Liu and Wang, and that's to compute by sort of descent from the relative case of S adjoin Z. So if you think of the Amatzer complex or the descent complex of this, I'll call this Z0, Z0, Z1, if I take the check complex of this map, then faithfully flat descent tells me that the totalization of this cosimplicial object gives me back the sphere spectrum. Okay. Now, what we're going to do is we're going to take the ring OK we want, and we're going to map this whole cosimplicial diagram to it just by sending each zi to pi. That's something we're allowed to do. And now the sort of claim is that then there's descent for all of the theories that we wrote down relative to these rings. So then for example, THH of OK mod pi to the n, which is sort of the relative THH of OK here, is the tot of the THH of OK mod pi to the n over S adjoin Z, Z bullet, I guess I'll write. Okay. And the same is true for TC, TC minus, and TP. So this was already used, this descent was already used by Liu and Wang to compute the K-theory of local fields with FP coefficients, revisiting this work of Hessel, Holt, and Madsen. And so we use the same idea, but we have this tweak, which is that we realize motivic filtrations on each of these pieces that relate everything to relative prismatic cohomology. And now, so let me say one more sentence. Basically, what we can do, let's consider the problem of computing prismatic cohomology of R, the absolute prismatic cohomology of R. Oh, yes. Okay, well, let's just say we want to compute the absolute prismatic cohomology of R, which is the associated graded of this. That's GR0 TP of R. And so this is the totalization of the GR0s of TP of all of these, and that's this prismatic cohomology of R over these delta rings, ZP0 up to ZP, I don't know, S or something like that. That's what the associated gradeds of these are. And of course, we have to Nygaard complete and Frobenius twist here. These are all discrete. And they're prismatic envelopes in the sense of yesterday's talk. So this is actually a cosimplicial abelian group, not like a cosimplicial complex. But it's a cosimplicial abelian group converging to a complex with known cohomology, which means that it's exact starting at some point. Oh, it's still OK mod pi to the n. So this has cohomology in degrees 0 and 1. And that means that this cosimplicial abelian group is exact, or the associated cochain complex is exact starting in degree 2. And that means that you can compute this prism R just via, prism R over a single generator and prism R over 2 generators. And then you just, and really what you want to do is compute it here, but then land inside the cycles here. And then it's just the equalizer of this map. So here there's cycles from here to the next term. But what that says is that this is quasi-isomorphic to this 2-term complex. So if you can then compute everything in this picture, then you're done. Okay, that's the general strategy for what to do. And there's a couple tweaks to make this finite. This isn't really yet a finitistic strategy, but this is the main idea. And I'd better stop here. Thanks for your time. Um, it is complete in this case. It's complete. I guess I'm saying that is one way to deduce the upshot. Yes. Yeah, because it's like, yeah, right. It's actually even better. One can prove, um, one can prove that just, one can prove the following basically, that ZPIR for I positive is just equivalent to the filtration part 1 to IN minus 1 of ZPIR. Everything higher is just 0, it turns out. And we'll see why tomorrow, yeah. Yeah, I agree. It's not, probably it's not necessarily complete. Well, right. But, so maybe mod P, well, okay, yeah. Yeah, Jonas. Ah, well, you mean why isn't it Nygaard complete? Um, yeah, I do want it Nygaard completed. Sorry, thanks. Yeah, but as maybe not everyone heard what Achim said, but somehow the F completion is the same as the Nygaard completion in these cases. And in the end, we're only going to care about finite F filtration, so it's just going to be a non-issue computationally. Thanks.